Let's take a look at Riemann sums in section 5.3. So a Riemann sum is a way to approximate a definite integral. So again, let's start with a motivating question, an application on our trip here from Anchorage to Badger. Now, before we assumed that we used the average velocity on the trip. So we just took the total distance divided by the total time, and we have our average speed. So in that case, we were just finding the area of our rectangle. But we know that that's not really the case, right? We know that on our trip from Anchorage to Badger, we increased and decreased in speed, right? So maybe the trip looks more like this kind of in general. So then the total distance, the 369 miles, is the area. Okay, so the area is the total distance. But how do you find the area when the velocity is shaped like this? We don't have formulas anymore. We don't have base times height. We don't have 1/2 times base times height for a triangle. And that is why we need all of the calculus that we're going to talk about. But the thing to do is probably, and it's what happened historically, is you just approximate it the best that you can. Okay, we approximate it the best that we can in little rectangles. And one of the ways that you could think about doing this is like, okay, there's a bunch of time that it took. It took 6 hours and 40 minutes. And we knew the velocity at every point in the trip. But let's split our trip into, let's say, minutes or even seconds. So every second of the trip. Okay, we're imagining, I know there's a lot more seconds than what I'm graphing here, but every second of the trip, we knew exactly the speed that we were traveling. So then a pretty good approximation for the distance then is to find the total distance that we traveled in every second rather than the whole trip altogether. So we could find the total distance that we traveled in the first second. We could find the total distance that we traveled in the second, so on and so forth. Find the total distance that we traveled in the third second. And you do that for the entire trip, and what you see is that the distance traveled over every second, all added up, is very close to the total distance that's underneath the entire graph. So that is an approximation. We're going to call the sum of all the rectangles a Riemann sum. Okay, we're going to call it a Riemann sum. And a Riemann sum is the way to approximate the area under the graph or below the graph if the area is negative with these little rectangles. Now, you'll notice there's an awful lot of them, and there's hundreds, thousands of them perhaps. So we're going to want to use something like a computer to actually add them all up when there is this many of them. Or we could somehow get lucky and find another way to find that area using antiderivatives, which is what we're going to talk about in the next section. But in this section, we're just going to think about approximating these areas with these rectangles. So before we get into the technical details of the math and the notation that we use, this is how you're thinking about what we're doing. It's a very natural thing to try to do. We want a total distance, or we want a total quantity. We know the rate at every tiny little bit of time, perhaps. We want to know the total quantity, and that this is just a way to approximate what that total quantity is by adding up the tiny little quantities in each little bit of time. Okay, so in order to do that, we need to add a whole lot of things. We need to be able to add things in a way that's organized, in a way that's descriptive. So we need summation notation. Okay, so here is kind of an introduction to sequences and series, which we're going to be talking about later in class. But here we are talking about a sequence. So the sequence that we have is a little I is equal to 2i minus 1. And that's a way to define a sequence of numbers. There's a first one. Right? The first one is when you put 1 in for I and you get 2 minus 1, which is 1. The second one is when you put 2 in for I, you get 4 minus 1, which is 3. The third one is you put 3 in for I, and you get 3 times 2 minus 1, which is 5. And you can see that this is just a way of enumerating the odd integers. So we have 1, 2, we have 1, 3, and 5. So then the question here is, how do we talk about number 1? Well, number 1 is the sum. I goes from 1 to 6 of AI. This is called, I is called an index variable. And all it does is it tells us what position we are in the sequence that we're adding up. Okay, the sigma sign means add. Okay, that's what that, this is the sigma notation. And it means to sum or add. Okay, and so how do we interpret this thing? Well, this means start at 1 and go to 6. When I is 1, so A1 plus A2 plus A3 plus A4 plus A5, and then 6 is where we stop, plus A6. And so that's shorthand notation for just writing that. Now, what is that? Well, we could do it the long hard way. We're going to have some formulas for this. But you just write down each thing. We know that this is 1 plus 3 plus 5 plus 7 plus 9 plus 11. Okay? Now, this is a geometric sequence. Okay? And there are nice ways to add something like this up. This is really just 12 plus 12 plus 12, which is 36. Okay, so that is a shorthand way to write a sum. Let's take a look at the next one, which is just a little bit more complicated. Here I is going from 3 to 7 of 3ai minus 4. And again, writing this out longhand is kind of annoying, and that is why we have this better way of doing it. Now, if we were to write this out longhand, we start with 3 this time. So this is 3 times a little 3 minus 4 plus 3 times a little 4 minus 4. Do you see the only thing changing is I? I is changing, starting at 3, going to 7. Plus 3 a sub 5 minus 4 plus 3 a sub 6 minus 4 plus 3 a sub 7 minus 4. Okay, and so that's really what that notation stands for. Now we can see though that if we were to, we could do a little bit of shuffling around to make the math easier here. We could group all of the A1 or A3, A4, A5, A6, A7. They all have a 3 next to them. So we could write this as 3 A3 plus A4 plus A5 plus A6 plus A7. And then we have minus 4. In this case, we have it 5 times. Minus 4, minus 4, minus 4, minus 4, minus 4. But this really is just 3 times the sum. 3 goes to 7 of AI minus 5 times 4. Or what we could write is plus 5 times negative 4, because there are 5 negative 4s. And we can see that we want to get to a place eventually where we just go straight from here to here. Okay, we are just using properties of sums. We know that when you have a constant factor, you can pull it into the front of the sum, and we want to be able to, excuse me, not have to write down all of these terms. Now, to do this, this is, we still have to find, we've kind of simplified the sum. We haven't actually found it yet, right? So this is A3, right? A3 is 5. That's the third odd number. So this would be 5. A1 is 1, right? A2 is 3. A3 is 5 plus 7 plus 9 plus 11 plus 13, right? Minus 20 in this case. And there we have, looks like we have 18 plus 18 plus 18, which gives us, let's see, 3 times 3 times 18s, which is 30 plus excuse me, 30 plus 24, 54 minus 20. Okay, so this here we have 150 plus 12. So here we have 162 minus 20, which is 142. Okay, so that's how we can do a sum like number 2. So these take practice and they take some familiarity, but try to write it all out the first time, the first 10 times you do it. Then you'll see the reason for this notation. It just saves time. And you're just doing sort of addition anyways. That is summation notation, okay? And I'll repeat myself and just say that it just takes some time to get used to. So we have properties of sums. They should be kind of reminiscent of properties of the integrals that we have, where if you're just going to add up a constant a bunch of times, we just saw this. If you're going to add up -4 a bunch of times, that's what multiplication is. Multiplication is just what you get when you add up the same thing a bunch of times. Okay? And then if you have a constant times everything, right, like we did above, we had 3 times our arithmetic sequence, then you can just factor out that constant. Okay, so these statements, they look complicated, they look fancy. They're really just saying the same thing that you already know about how we work with numbers. And some of the other properties here, do look at the videos in the read in the text for examples. But this just says you can sum up the first bunch. This in number 4 here. Number 4 says sum up the first bunch of them, right? And then sum up the next bunch, and that's the same thing as summing them from the start. So going from m to j and then j plus 1 to n is the same thing as summing from m to n. Okay, so what these are saying are really not that sophisticated of a thing, but they're very handy rules to have around. Now, numbers 5, 6, and 7 are actually formulas. So they're a little bit different than the other ones, because these are kind of handy formulas to have around. They tell us how to sum, right? The consecutive integers, consecutive squares, and consecutive cubes. So, for example, in number 5 here, this tells us what if we want to sum going from 1 to 100 of I. Well, that's 1 plus 2 plus 3 plus all the way up to plus 99 plus 100. And this tells us a formula for it. Okay? Now, there's fun ways to think about this, but the formula says to take n, which is 100 in this case, multiply it times n plus 1, which is 101 in this case, and divide it by 2. Right, so you end up getting a 50-50 here. So that it's you don't have to do it 1 plus 2 plus 3 and then do it the hard way. We have this formula kind of encapsulates a nice way of thinking about adding up consecutive integers. And this for the same way, number 6 and 7, consecutive squares and consecutive cubes. Okay, so back to integrals and the definite integrals. We're trying to find area under curves because that is how you take velocity and then get distance. Well, not all curves do we have easy formulas for, so we have to approximate them with these little rectangles. Well, in this case, we have a parabola, and it's giving us a few different ways to think about it. Okay, we can see that if we approximate it with this first one, that's called the right-hand rule, because the height of the rectangle is determined by the right side of the subinterval. Okay, and when I say subinterval, I'm talking about this bit right here. That's like the subinterval. And we're going to call that delta x, right, in our notation later. And that subinterval, so the base is kind of determined by what delta x is, The height is determined by the height of the function. Well, we have a lot of choices to make. Is the height of this rectangle going to be the height at the right endpoint, or is it going to be the height at the left endpoint? This one's called a right-hand rule because the height of the rectangle is determined by the right-hand side of the rectangle. Now let's take a look at the next one in contrast. Over here, we still have our delta x, but the height of the rectangle is not determined by the right hand, right? If it was determined by the right-hand rule, that would be the rectangle. But it's not. If it was determined by the left-hand rule, that would be the height of the rectangle. But it's not. Instead, it's determined by the midpoint. So we call this the midpoint rule because the height of the rectangle is determined by the midpoint. And then over here we have the left-hand rule because we can see the height of the rectangle is determined by the left-hand side. And then there are other nice rules to have. Okay, so those are kind of the options that we're going to be looking at least at the beginning here, for Riemann sums. Now, in this particular example, it's saying don't divide it up into 4 chunks, divide it up into 16 chunks. So we would have 1/4 would be our delta x, right? Our delta x is here, and it would be 1/4. And then you would divide each of these. So we'd have a total of 16. This one's not very even. They don't have to be evenly spaced out all the time, which you can see in the reading when it's defining the partitions. So there we're dividing it into total of 16 pieces. This is like the initial example where we were looking at, we had a whole trip that was 6.6 hours long, and we divided it into seconds, so tiny little bits. And that says we can use the left-hand rule, or the right-hand rule, or the midpoint rule. Now, if we were to use the right-hand rule for each of these, that would look like this, right? We go to the right-hand side, and we will get a rectangle here. In the next subinterval, we'd go to the right-hand side and use this. The third subinterval, the height is determined by the right-hand side. So that's what I've drawn so far is the right-hand rule. And there's a subtle difference here between the right-hand rule and the left-hand rule. And you can see there's a shift that the F, this is using the, this would be in our case, this would be, I'm just going to zoom in a little bit here, just to match up with the notation. This would be x0, x1, x2, x3, x4, x5, and so on, x7, x8. So when the function says x sub little I starting at 1, that's the height of the function. So this is the height of the function on the right-hand side. However, on the left-hand rule, see how it's shifted 1 to the left. So the height of the function would be determined on the left-hand side of the subinterval. And how does that matter? Well, 1 you can see is kind of an overestimate, and 1 is kind of an underestimate, because the rectangles either don't contain the whole graph underneath, or they contain some space above it. Now, the midpoint rule is like a compromise. Okay, the midpoint rule is like a compromise that says, let's just find the midpoint, and you can see that that's the average, right? So you find the x value that's in the middle. That's what this would be right here. Right, you find the x value that's in the middle of each subinterval, and that determines the height. And so that's what the midpoint rule is. Okay, and that's generally how you can find Riemann sums, or how you think about them anyhow. Now, when you have actual functions that are difficult, let's take a look. Here's an example that the function is this function right here, sine of 2x plus x over 3. And this is a Desmos tool, which I'll share with the class, that helps us find Riemann sums and helps us visualize them. Now, let's take a look at it. Let's just from 0 to 3. So we'll move our left-hand bound to 0, and our right bound is 3. So we're trying to estimate the total net area to this graph from 0 to 3. Now down here you can see n equals 12, so that's the number of subintervals. So that means that we're going from 0 to 3, So we're chopping each subinterval into 4 pieces. So here we have, between 0 and 1, we have 4 rectangles. And now this part down here is asking us if we want the left-hand rule, midpoint, or right-hand rule. And right now it's equals to 0, so it's using the left-hand sum. If we wanted to use the right-hand sum, we can change that to 1. Whoops. Change that to 1. Now it's using a right-hand sum. The midpoint rule, 0.5. And now we can see we're using the midpoint rule. And if we want more subintervals, we can change n to be greater and greater. And you can see that the more subintervals we have, the better we are getting as an approximation to the actual area under the curve. Now, this tool, since it's a computer, can add up all these numbers. It's finding us for us. So right down here, that is the Riemann sum, this I, okay? And we can see when n is very small, it's a rather crude estimate. But as n gets rather large, you can see that the decimal places are only changing very far down here. So as n gets large, we're approaching you might say the limit as n goes to infinity is approaching the actual net signed area. And that's exactly what's happening mathematically, is the limit as n goes to infinity is what we call the definite integral. So the exact value of a definite integral is a limit. Okay? And this helps us approximate that limit, this tool. So that's kind of a short introduction to Riemann sums. Now you might be asked to do some problems like this and do it by hand. So you can see Riemann sums involve a lot of sums. We want to generally avoid unnecessary computation, but we want to be able to use the mathematical notation to express things in general. But when you have problems like this, I kind of suggest using a technology if you can. And you can change our function. Let's change it to 2x plus 2. Okay, so that's a line. So we could find this exactly. We do not need to estimate this with a Riemann sum, but just for the sake of the problem, we can. And we're going from -2 to 1. So this is the area. This is the net area that we're estimating. And we would like to use the midpoint rule. So it's already set on the midpoint rule. And if we take n down, we can see this is using the midpoint rule for various values of n. And we are approaching the actual area under the curve. Now, notice that no matter which value of n, we have I equals 3. That's because we have a certain kind of symmetry when you have a line. And the midpoint rule is perfect for it because the amount that it makes up for is the amount that it loses. So because this happens to be a line, we're getting the exact value of the definite integral for every value of n, which is pretty cool.